Hello and welcome to Science Talk. I am your host, Jim Massa. In this video, I wish to share with you two major studies, two major reports. The first one is the world headed for an ice apocalypse? The rapid collapse of Antarctic glaciers could flood coastal cities by the end of this century. There are two glaciers. Okay. These glaciers, named Pine Island and Thwaites, have been steadily marching towards the Amundsen Sea, which is part of the Southern Ocean. Further inland, the glaciers widen into a 2-mile thick reserve of ice covering an area the size of Texas. There's no doubt this ice will melt as the world warms. The vital question is when. The glaciers of Pine Island Bay are two of the largest and fastest melting in Antarctica. Together, they act as a plug holding back enough ice to pour 11 feet of sea level rise into the world ocean, an amount that would submerge every coastal city on the planet. And for that matter, bye-bye Florida. For that reason, finding out how fast these glaciers will collapse is one of the important scientific questions in the world today, and something you just don't hear about. So to figure this out, science has been looking back to the last ice age, about 11,000 years ago, when global temperatures stood at roughly their current levels. Bad news? There's growing evidence that the Pine Island Bay glaciers collapsed rapidly back then, flooding the world's coastline, partially the result of something called marine ice cliff instability. There's a couple things going on, as I'll further describe here. You not only have the warmer temperatures on the surface that can melt the surface of the ice, but as you're warming the oceanic waters themselves, you have warmer oceanic water coming in underneath and will melt the ice from below. Sometimes as a glacier protrudes past the shoreline onto the ocean, the bottom of the ice is sitting on the bottom of the ocean. Obviously it's not very deep, and it's supported then. You start to melt that, and now you're only relying on the water to support the weight of the ice, and something that isn't enough, and then that will crack and break and fall down. That then allows, when it's grounded in the seafloor, the glacier is kind of slow moving behind it. You create a situation where that is broken and that moves off. Now these glaciers back here can rapidly increase their rate of movement towards the sea. So that's part of what's going on here. Ocean floor gets deeper towards the center of this part of Antarctica, so that each new iceberg that breaks away exposes taller and taller cliffs. Ice gets so heavy that these taller cliffs can't support their own weight, and they come down. So when you reach a critical height, the ice will come down. Kristen Poignard, a glaciologist at NASA's Goddard Space Flight Center, says we need to know how fast it's going to happen. In the past few years, scientists have identified marine ice cliff instability as a feedback loop that could kickstart the disintegration of the entire West Antarctic ice sheet this century. Ice comes in many forms. Okay, if you look at sea ice, for example, we have frazzle ice, and we have Bergy bits. We come up with these names here, and then you have 1-year ice, 2-year ice, 3-year ice, so on for that's sea ice. This is glacially derived here. Floating ice, like the kind that covers the Arctic Ocean, doesn't raise sea levels because it's the seawater itself freezing. So the level's not going to change. Land-based ice, however, is a different story. That melts. That is water added to the ocean. That will raise the ocean levels. Antarctica is a very large place, about half the size of Africa, roughly the size of the U.S. probably. The snows in the interior of the continent roughly matched the icebergs that broke away from glaciers at the edges. So, in other words, the continent's ice was in relative balance. Wherever snow was introduced in the interior equaled the amount that broke off. Well, the balance is now changing, okay, due to the warming activities. A wholesale collapse of Pine Island and Thwaites would set off a catastrophe. Giant icebergs would stream away from Antarctica just keep on coming. High tides would get higher, which would then further bury any shorelines, right? Inundates further inland. Right? And it can create hundreds of millions of climate refugees. This can happen within 20 to 50 years, which is way too fast for humans to adapt. With marine ice cliff instability, sea level rise for the next century is potentially much larger than we thought it might be 5 or 10 years ago. Again, that's what Dr. Ponar says. Like everything else, as you get more data, you have a better understanding of things, you can reassess. A lot of this newfound concern is driven by the research of 2 climatologists, in addition to Dr. Ponar's work, Rob DeCanto at the University of Massachusetts Amherst and David Pollard at Penn State University. A study that they published last year in Nature was the first to incorporate the latest understanding of marine ice cliff instability into a continent scale model of Antarctica. Their results drove estimates for how high the seas could rise this century, even higher. The headline of their study is as follows: Antarctic model raises prospect of unstoppable ice collapse. I said this is in Nature, and Nature is not exactly known for publishing hyperbole. Instead of a 3-foot increase in ocean levels by the end of the century, 6 feet was more likely, according to DeCanto and Pollard. But if carbon emissions continue to track on, basically continue on doing nothing to change things, i.e. continue with the status quo, it could rise a full 11 feet if all the ice in West Antarctica is freed up. So we're looking at 3 to 6 to 11 foot rise in sea levels is basically what they're predicting. Any of which would be bad. A 3-foot sea level rise would lead to more frequent floodings of U.S. cities such as New Orleans, Houston, New York, Miami. Pacific Island nations like the Marshall would lose most of their territory. The Maldives would probably disappear altogether. Unfortunately, it now seems that 3 feet is possible only under the rosiest of scenarios. That's not encouraging. At 6 feet, though, around 12 million people in the U.S. alone would be displaced. World's most vulnerable megacities, Shanghai, Mumbai, Ho Chi Minh City, could be wiped off the map. At 11 feet, the land currently inhabited by hundreds of millions of people worldwide would end up underwater. South Florida would basically disappear, be largely uninhabitable. Floods on the scale of Hurricane Sandy would strike twice a month in New York, the high tides, in New Jersey, as the tug of the moon alone would be enough to send tide waters into homes and buildings. DeCanto and Pollard's breakthrough came from trying to match observations of ancient sea levels at shorelines around the world with current ice sheet behavior. Around 3 million years ago, when global temperatures were about as warm as they're expected to be later this century, oceans were dozens of feet higher than today. Previous models suggested it would take hundreds or thousands of years for sea level rise of that magnitude to occur. But once they accounted for marine ice cliff instability, DeCanto and Pollard's model pointed toward a catastrophe if the world maintains a business as usual path, that is, we don't reduce carbon emissions, then we could get this scenario of up to 11-foot rise within a considerably shorter period of time. So, it could happen faster or slower, we just don't really know at the moment. But, like everything else, you need to get more information, more studies, more data to analyze. The new evidence that once a certain temperature threshold is reached, ice shelves of glaciers that extend into the sea will begin to melt from both above and below. That goes back to the point I said at the beginning of this video of you have melting from below, the warmer oceanic waters, melting from above, the warmer oceanic waters melting it from below. These two taken together will increase the instability of the glacier, making it more likely to break, collapse much sooner. The only place in the world today where you can see ice cliff instability, and basically a place where we can then observe what's happening there and then extrapolate to what's happening in Antarctica, is at the Jakobshavn Glacier in Greenland. It's one of the fastest collapsing glaciers in the world. The Kantos stated that to construct their model, they examined the collapse rate of Jakobshavn, cut it in half to be extra conservative, then applied it to Thwaites and Pine Island. There is reason to think, though, that Thwaites and Pine Island could go even faster than Jakobshavn. Right now, it's a floating ice shelf protecting the two glaciers, helping to hold back the flow of ice into the sea. But recent examples, like the collapse of the Larsen B shelf on the Antarctic Peninsula, show that once ice shelves break apart as a result of warming, their parent glaciers start to flow faster towards the sea, an effect that can further weaken the stability of ice that's further inland as well. If you remove the ice shelf, there's potential in not just ice cliff instabilities to start occurring, but a process called marine ice sheet instabilities will take place. And that was stated by Matthew Wise, a polar scientist at the University of Cambridge. Professor Wise continues to state, this signals the possible rapid destabilization of the entire West Antarctic ice sheet in this century. Once the stresses exceed the strength of the ice, it just falls off. Not just Pine Island Bay. Other glaciers around Antarctica can be similarly at risk. And of course there's Greenland, which could contribute as much as 20 feet of sea level rise if it melts. So, it's quite alarming, but like everything else, scientists like to debate. Ted Scambus, he's a lead scientist at the National Snow and Ice Data Center in Boulder, Colorado, says that the new research by Wise, DeCanto, and Pollard, while he said it's certainly tantalizing, he said he does not think the research establishes how quickly it can happen. And if you look at the comments of Wise, DeCanto, and Pollard, they're basically stating, yes, we think that it could be it could be anywhere 20 to 50 years, we're not sure the time frame, but we are proceeding to refine our models and better ascertain that. So it's a fair criticism. But like everything else in science, collect the data, do continued analyses, and see where it takes you. Now, the Scambos does say something that's interesting. He said, even if Thwaites or Pine Island collapse all at once, he thinks that it would produce a whole bunch of iceberg that could act as a temporary ice shelf, slowing down the rate from behind. So that a lot of that would depend on the bathymetric conditions of that region and whether the icebergs will ground onto the seafloor or not. But it's an interesting idea, and it's something that we would have to see to answer that question. The takeaway message is that ice cliff instability, the melting of the ice from above and below, causing ice to rapidly break off, it then falls into the ocean, currents take it away into warmer waters where it melts, and you start putting all of this into the ocean system, you start melting, you start increasing the sea level. That's basically what they're saying is likely to happen. The next story involves the Arctic ice. So I'm going from one end to the other end of the planet. The Arctic shows no sign of returning to the reliably frozen region of past decade, according to NOAA, National Oceanic and Atmospheric Administration, annual Arctic report card. The 2017 report card primarily covers the period from October 2016 to September 2017, 12-month period. NOAA releases a report card each December to sum up the previous October to September year in the northern latitudes. That's a thing, that's a report that they publish every year. It looks at the previous October to September, and basically they're collecting the data from October, September, and then the next October and November they're analyzing and writing up analyzing data, writing up the report, which then gets released in December. The report card puts the year's developments into context with the longer-term trends observed in the region. After this past Arctic summer, which was relatively cool in the context of the past several decades, this past Arctic summer failed to produce stable sea ice or other positive indicators of a healthy average ecosystem. Healthy ecosystem in the sense of what has been traditionally been the situation. The authors of this year's report card suggest that the region has reached a new normal of thin, weak sea ice. New normal. That means that it's basically stating a new set of conditions that will become the new standard. The other thing you have to keep in mind, and this applies also to Antarctica as well, you have ice. That's a nice white surface. White surface reflects heat back into space. It's called the albedo. By reflecting heat back into space, it keeps the planet warm. So Antarctica is sort of like a big refrigerator for the planet because the big ice sheet reflect that heat back into space. You start losing that ice, instead of the heat being reflected back into space, you decrease the albedo, you're now increasing the heat that is absorbed. Not only does that change weather patterns, air mass movements, and so on, and oceanic temperature, you're just going to increase the temperature of the planet worldwide. Well, you have the same thing going on in the Arctic. If you reduce whether it's the winter sea ice maximum extent or the summer minimum ice extent, if you reduce the amount of sea ice that's there, you're reducing what heat can be reflected into space. Now if you have more and more open water, that open water is going to absorb that heat, not reflect it. It's going to warm the ocean up, in this case the Arctic Ocean. So we have that effect going on. So not only are we seeing, you're going to increase sea level, you're going to increase the heat that's absorbed. You're going to make for more stormy conditions because the heat in the water is going to be distributed somehow. So what has happened is for many thousands of years, Earth was sort of in an equilibrium state. Human activity has now perturbed the system, and Earth is trying to find its new equilibrium point or new equilibrium condition, but because the system continues to be perturbed by human activity, is leading to the extremes in the conditions that we're seeing, extreme temperatures. It could be, 15 degrees in Boston one day and drop 10 inches of snow, and the next day it's 55 degrees and it all melts. You see some wild swings in conditions. So you have to consider that as well. The albedo. How is the heat being absorbed or reflected? Typically, we construct what's called heat budgets. We look at the incoming solar radiation, typically in the UV band, and we look at the outgoing solar irradiation, what's reflected back into space. That's typically in the infrared band. Then we look at what heat is absorbed, how is the heat used, what happens to the heat and transfer, and all that kind of stuff. Then we construct heat budgets. So a lot of the work utilizes heat budgets to ascertain what's happening with water temperatures as an example. So continuing on, even cool years are now unlikely to return the Arctic to its healthy status quo, what was previous. The region is just too damaged to go back to what was previously considered to be normal. This is not me stating it. This is coming from the report. This is what the NOAA folks are saying. And again, scientists are not necessarily known for hyperbole or for wild exaggeration. They're basically stating that we got serious stuff going on here. Arctic paleo reconstructions, which extend back millions of years, indicate that the magnitude and pace of the 21st century sea ice decline and surface ocean warming is unprecedented in at least the last 1,500 years and likely much longer. Surface ocean warming, that's just what I was just stating, that if you remove the ice, the ocean waters now absorb the incoming heat. To understand the Arctic climate, you have to understand its 4 key elements: air, water, land, and ice. So now let's consider each of those. So here's what happened with each of those aspects, air, water, land, and ice, from that 12-month period of October 2016 to September 2017. Let's first start with the air. Last year's 2015 to 2016 report card showed that year was by far the warmest in observational records, which date back to 1900. The 2016-2017 period was significantly cooler, but still the second hottest year since 1900. So it was cooler than previous recent years, but still warmer when compared to historical stuff. So that, of course, is telling us that recent trends have been very, very warm. Most of the heat was packed at the beginning of the year, leading to a warm Arctic autumn and winter. Spring and summer 2017 was abnormally cool for the modern era. Summer, in particular, was kind of out of sync with recent trends. The only exceptional Arctic summer weather turned up in Alaska and northwestern Canada, Yukon Territory, where July was the warmest on record. Yeah, it was warm last July. Okay, moving on to the water. Sunlight drives warming in the Arctic Ocean. The water's temperature varies each summer with the amount of sunlight that makes it through the atmosphere and ice cover to strike the sea surface. When there's less ice, in other words decreased albedo, less cloud cover, Northern Ocean warms faster. In some areas, August 2017 was almost 5.4 degrees Fahrenheit cooler than August 2016, but 2017 sea surface temperature still was part of a long-term warming trend. August 2017 was 5.4 degrees Fahrenheit warmer than August 2012. Now 5.4 degrees Fahrenheit is basically 3 degrees Celsius. That's a big deal because 2012 saw the lowest summer sea ice minimum ever recorded in the Arctic. That long-term warming has sustained a bloom of life in Arctic waters as organisms ranging from algae to large predator fish move into waters that have once been too cold for them. Now I'm going to pause right there and give you a little background on what's meant there and what's going on. Typically where you have the sea ice, as the sea ice melts, okay, you have that water being added to the surface. There's a little bit of mixture going on. And typically we get what's called ice edge bloom effects, where the conditions are created where algae, phytoplankton, whatever, can engage in photosynthesis, and they start to do what they do, and they create a little bloom, and then you have zooplankton coming in, little fish, and so on and so forth. Okay. The statement here that move into waters that have once been too cold for them. Typically speaking, in the Bering Sea, through the Bering Strait, into the Arctic Ocean, Chukchi Sea, Beaufort, what have you, the predominant phytoplankton group would be diatoms. Diatoms are a cold water phytoplankton. But, of course, like anything else, only certain organisms that are well adapted for such conditions will do well in cold conditions. Well, now we're warming up the surface waters, not just in the Arctic Ocean, but in the Bering Sea. There has been documented a regime shift in the phytoplankton species found in the Bering Sea. Basically, a shift has been from diatom to coccolithophorids. Coccoliths we call them for short, because coccolithophorids is a mouthful. But coccolithophorids are a phytoplankton group that prefer warmer waters. So we're seeing this regime change. And that's kind of what they're alluding to here. So, again, going back to the point, when you start warming up water that significantly, that's a lot of energy to do so. And now we're seeing changes in basically the structure of an ecosystem. Moving on to the land. Permafrost. Permafrost is that frozen layer, frozen earth that's found in northern latitudes. The permafrost is warming and softening, thawing out. Okay? In summer 2016, the permafrost, 20 meters below the surface, 66 feet approximately, reached its warmest temperature since 1978. All around the Arctic, the ground has gotten mushy as thicker and thicker layers of slush form beneath the earth. Okay. This will impact roads and buildings. I discussed this in a previous video. At the same time, in 2015-2016, there was a spike in apparent quote-unquote greenness in the Arctic, areas that look green in satellite view because of plants doing well. One of the things that we're seeing as the Arctic warms is that tundra plants are being replaced by low bush plants like low-lying willows and so on, because tundra plants, they don't need to extend their roots deeply into the ground. But these other plants like the willows and so on, they need a deeper soil to extend their roots into. So the fact that they're moving north is indicative of the fact that the permafrost is indeed thawing, that the ground is indeed softening, enabling, allowing these plants to extend their roots and then take hold. It's basically what's going on here. The last aspect, and this is probably the most important element of the Arctic, is the sea ice. When the sea ice is expansive and healthy, it keeps the oceans from warming and reflects the sunlight into space, protecting the whole planet from warming, just as it does in Antarctica. That's the albedo that I've been mentioning. Arctic sea ice pulses every year, growing each winter to double or triple the extent in the previous summer. In recent decades, though, it's been a state of overall decline. Scientists have been telling us that the first completely ice-free summer in the Arctic is on its way. I think we even saw that recently. Now it's the official position of NOAA that the Arctic shows no signs of ever returning to its year-round, comfortably or typically iced-over state. Winter 2016-2017 saw the lowest maximum sea ice extent in satellite records dating back to 1979. Third record low year in a row. Sea ice maxed out on March 7, 2017 at 5.5 million square miles, 14.2 million square kilometers, 8% below the 1981 to 2010 average. Remember, for oceans, March is the depth of winter. March is typically the oceanic winter. Since then, sea ice then started to shrink 5 days earlier from the 81 to 2010 average, reaching its summer minimum on September 13th at 1.8 million square miles, 4.6 million square kilometers. That extent was slightly greater than the 2016 minimum, 25% lower than the 1981 to 2010 average. The 10 lowest September extents have occurred in the last 11 years. Right there. That's telling. Let me state that again. The 10 lowest September extents have occurred in the last 11 years. In any given month of the year, they calculated sea ice extents are declining at a rate of about 13.2% per decade. The ice that remains is also thinner, younger, and less stable than it's been in the past. They're referring to what's called multi-year ice. Back in the 1980s, just 55% of the peak ice each winter was new that year, and 16% of the ice had hung around for more than 4 years. In other words, the seawater would freeze, and that ice would not melt for 4 years. Well, now we're not seeing that. Seawater is freezing, but the ice is then melting. It's not persisting. In 2017, a full 79% of the winter maximum was made up of newly frozen ice, and only 0.9% of the maximum was more than 4 years old. Basically, this is telling us that there is less and less multi-year ice seen in the Arctic. That's what this is telling us. When ice doesn't age, it doesn't have time to get thick. That long-term thinning trend weakens the ice, making it more difficult for it to stabilize or grow during cooler years, with long-term implications for the health of the Arctic and in turn the entire planet. Things are happening, and basically if you look at both ends of the Earth, the Arctic and the Antarctic region, this is where we're seeing some of the biggest changes. Both the sea ice in the Arctic Ocean and the Antarctic ice sheets traditionally have reflected a lot of heat energy back into space, acting as basically a refrigerator for the planet, keeping it cooler. As we lose the ice in both regions, the albedo will decrease, more sunlight energy will be increasing even more so, and resulting in rapid warming of the planet. That brings me to the end of this video. I thank you for your time. I hope you found it informative. We'll talk again soon.